Welcome students. In this video we will discuss about open channel flow. Let's start. Flow in open channels means flow of liquid with a free surface. That means surface is exposed to a constant pressure, which is the atmospheric pressure. So that is called flow in open channels. Okay, in the figure you can see a channel where there is a liquid flow and it is exposed to atmosphere. So that surface is called a free surface. In case of open channel flow, flow takes place under the force of gravity. That means there is no external force for the water to flow. It flows under the force of gravity. That means the channel bed, that means the bottom of the channel. This is the channel. You can see the channel in the figure, and for the flow to take place under the influence of gravity, the bottom bed of the channel must have a slope. Okay, and also the hydraulic gradient line which we have seen before, the HGL, it coincides with the free surface of water. Free surface is a surface which is exposed to atmosphere. That means on that surface the fluid is under constant pressure, which can be atmospheric pressure. Let's see the classification of flow in channels. We have four types of classification: steady and unsteady, uniform and non-uniform, laminar and turbulent, and subcritical, critical and supercritical flow. We will see one by one. First, steady flow and unsteady flow. So if the flow characteristics such as depth of flow, velocity of flow, rate of flow, which is the discharge, that is measured in meter cube per second. So all these quantities at any point do not change with respect to time. That means here we have dou v by dou t. There is variation of velocity with respect to time. That is equal to 0. Dou q by dou t, where q is the discharge or rate of flow, dou q by dou t is equal to 0. And dou y by dou t, which is where y can be called as the depth of the flow, that is also equal to 0. In these conditions the flow can be called a steady flow. That means flow characteristics at any point do not change with respect to time. And unsteady flow is where the flow characteristics at a point is not constant with respect to time, or it is changing with respect to time. That is indicated by these equations. So this equations representing unsteady flow. Next, let's see the second type of classification, which is uniform and non-uniform flow. So for a given length of channel, that is for a given length of channel through which the fluid is flowing, if the velocity, depth and slope of the channel and cross-sectional area of the channel are constant, it is called a uniform flow. That is for a given length of channel. Length is denoted here by S. So S is the length of the channel. That is, S is the length of the channel through which fluid is flowing. So along this length of the channel, or at all points or along the length of this channel, if the velocity, depth and slope and cross-sectional area of the channel are constant, the flow is said to be uniform. The slope of the channel is the entity which causes the flow under gravity. If there is a slope for the channel, the flow can be under gravity. Okay, and open channel flow is under gravity. Okay, and on the other hand, if all these quantities, that is velocity, depth, etc., do not remain constant along the length of the channel, the flow is said to be non-uniform. So you can see here the examples. Depth of the channel or depth of the flow is constant with respect to length of the channel, and velocity of flow is constant with respect to the length of the channel. So we say that this is uniform flow. Here depth of the channel or depth of the flow is not constant with respect to length of the channel, and velocity of flow is not constant with respect to length of the channel. So we call this as a non-uniform flow. Next, we will see about non-uniform channel, which can also be called as varied flow. Okay, so there are two types of non-uniform flows or varied flows, that is rapidly varied flow and gradually varied flow. So let's see what are they. Rapidly varied flow is defined as the flow in which depth of flow changes abruptly over a small length of the channel. Abruptly means suddenly. So that means depth of flow changes suddenly over a small length of the channel. So if you see this figure 16.1, you can see that there is a channel where there is flow, and here the depth of flow is this much, and here if you see there is an obstruction, there is some kind of obstruction to the flow which is here. So the depth is only this much, that is the depth is reduced and it is occurring suddenly. Here it was this much, then it was at this point it was more, very high, at this point it is less, at these points it is even lesser, again it increases though. So there is rapid change in depth of flow suddenly over a small length of the channel. This change occurs over a small length, that is a short distance. Okay, that kind of flow is called a rapidly varied flow. So when there is any obstruction in the path of flow of water, you see that there was an obstruction here, right? The level of water rises above the obstruction and then falls again and again rises over a small length of channel. You can see that that is what happened here. The flow was coming in this direction. We had an obstruction here and the flow, it rised above the obstruction and then it fell down and then again it rised up. Okay, thus the depth of flow changes rapidly over a short length of channel. Depth changing rapidly over a short length of the channel. Okay, so this is called rapidly varied flow. And if we see gradually varied flow or GVF, the depth of flow in a channel changes gradually over a long length of the channel. So that you can see here, this is a gradually varied flow. Here, at this point there is one depth. At this point if you see, depth is again slightly varying. At this point, depth has slightly increased. So at points 1, 2 and 3, depth of water is not the same, but it is not very different also. That is called a gradually varied flow. It changes, but it is changing only gradually and it takes place over a long length of the channel. Rapidly varied flow was happening over a small length of the channel. So if you see this channel, gradually varied flow occurs over this much length and rapidly varied flow occurs over this much length, right? Okay. Next classification is laminar flow and turbulent flow. So the flow in open channel is said to be laminar if the Reynolds number is less than 500 or 600. Okay, Reynolds number is indicated by the equation Re is equal to rho into V into R, the whole divided by mu. Here V is the mean velocity of flow of water. R is the hydraulic radius or hydraulic mean depth. That is cross-sectional area of flow normal to the direction of flow. Normal means perpendicular. So the area of the channel or flow which is perpendicular to the direction of flow. If we have a channel here through which flow is taking place, okay, flow is in this direction. So perpendicular to this direction of flow, what is the area of flow? So that area divided by the wetted perimeter. Wetted perimeter means perimeter or the length of the surface of the channel which is in contact with the fluid. Here in this figure, if we see, sorry, I will erase it. Okay. So if you have a channel with a trapezoidal cross section and you have water flowing through the channel, so this is the water surface or the free surface. So here this much perimeter of the channel is in contact with water. You can see here this perimeter of the water, sorry, of the channel is in contact with water. That perimeter is called the wetted perimeter. Okay, the channel you have here, and what area of the channel is in contact with the water, that is the wetted perimeter. So rho and mu are the density and viscosity of water. Wetted perimeter will be more clear when you do the problem. Okay. Then if the Reynolds number is more than 2000, the flow is said to be turbulent in open channel flow. That means 500 to 2000, the flow is considered to be in transition state. Okay, so there are three ranges of the Reynolds number. First is 500 to 600, where the flow is laminar. Next is more than 2000, where the flow is turbulent. And the third state, where Reynolds number is between 500 to 2000, so the flow is in transition state. Reynolds number is indicated by the equation rho E is equal to Re is equal to rho VR by mu, where V is the velocity, R is the hydraulic radius of the mean depth, which is given by the cross-sectional area divided by the wetted perimeter, and rho and mu are the density and the viscosity of water. Next classification is subcritical, critical and supercritical flow. So the flow in open channel is said to be subcritical if the Fruit's number is less than 1. Fruit's number is defined as Fe is equal to V divided by square root of G into D. V is the mean velocity of flow, D is the hydraulic depth of the channel, and it is equal to ratio of wetted area to the top width of the channel, that is A by T. Okay, this means A is the wetted area, there is a wetted cross-sectional area of the channel, and T is the top width of the channel. So if this is the channel cross-section, this is the top width, right? Okay, and wetted area is the area which is wet. Wet means in contact with the fluid. Okay. Subcritical flow is also called tranquil or streaming flow. So there are other names for subcritical flow, which is tranquil and streaming flow. Subcritical flow is where Fruit's number Fe is less than 1. Okay, and it is critical, that is the flow is critical if Fruit's number is equal to 1. Okay, and if the Fruit's number is greater than 1, the flow is called to be supercritical or shooting or rapid or torrential. So there are many names here. That is, the Fruit's number is given by the equation V by square root of G into D. The Fruit's number, if it is less than 1, the flow is called subcritical. If Fruit's number is equal to 1, the flow is called critical. If Fruit's number is greater than 1, the flow is called supercritical or shooting or rapid or torrential. Okay. So we have seen the different classifications of open channel flow. 4 different types of classifications were there. Next, let's see the discharge through open channel flow using Chassis formula. So consider a uniform flow of water. So the flow is uniform and the liquid is water in a channel as shown in figure 16.2. Okay, as the flow is uniform, it means that velocity, depth of flow and area of flow will be constant for a given length of the channel and at all points of time. So in this channel or in this open flow, here this is the channel bed and this is the free surface of water. So consider two sections 1-1 and 2-2. So 1-1 is here and 2-2 is here. So the notations are L, which is the length of the channel, A, which is the area of flow of water, I, which is the slope of the bed. So this is the bed. Okay, I is the slope. V is the mean velocity of flow of water. P is the wetted perimeter. That means the perimeter of the channel which is in contact with the fluid, that is water. And F is the frictional resistance per unit velocity per unit area. That means the resistance, frictional resistance to the flow. Okay. Weight of the water between sections 1-1 and 2-2 is denoted by W, and it is given by the product of specific weight of water and volume of water. Here specific weight is denoted by W. W is equal to rho into G, that is density into acceleration due to gravity. That is the specific weight. Volume is given by area of cross section multiplied by length of the channel. Hence W, that is the weight of the water between sections 1, and 2, is given by W into A into L. So now we know that W is the weight of the water. So this weight W is acting here at this point. Okay, so this is the horizontal, this is the bed of the channel. So this angle is I, which we have mentioned before. Angle I is the slope of the bed. Okay, if this angle is I, again this angle is also I. Okay, so if this angle is I, their weight of the water W can be resolved into two components. This is W cos I and this is W sin I. Okay, resolving W into two components, since this is angle I, because this angle is I. Okay, so W sin I is the component of weight in the direction of the flow or along the direction of the flow, that is W sin I. W can be replaced by small w into A into L into sin I. Then we have the frictional resistance, which is against the motion of water. So motion of water is in this direction. So frictional force will be in the opposite direction. So frictional force is given by frictional coefficient F into surface area into velocity the whole raised to n. Okay, that is the frictional resistance. So the value of n, it is found experimentally equal to 2. So an experiment was conducted and value of n was found to be 2. Surface area is equal to P into L. Okay. So frictional resistance against motion is equal to F into P into L into V square. Okay. Initially, frictional resistance was F into surface area into velocity the whole raised to n. Then experimentally, the value of n was found to be equal to 2. Surface area is equal to P into L, where P is the perimeter. So F into P into L into V square. So here, forces acting on the water between sections 1, and 2, are component of weight of water, which is W sin I, frictional resistance against flow of water, which is here, then pressure force at section 1, and pressure force at section 2. As depth of water at section 1, and 2 are same, so here depth is same because this is a uniform flow that we have said in the beginning. So depth of water is same. Pressure force are same. So we said that there are two pressure forces acting on the water between sections 1, and 2. Pressure force at 1, and pressure force at 2. They are the same and they are acting in opposite directions. That is, here pressure force will be acting like this, here pressure force will be acting like this. Okay. Hence they cancel each other. They got cancel each other. In the case of uniform flow, the velocity of flow is constant for the given length of channel. Hence, there is no acceleration acting on the water. Since velocity is a constant, there is no acceleration. Acceleration is the change in velocity with respect to time. But here velocity is constant, so there is no acceleration. Hence, the resultant force acting in the direction of flow must be 0. So there is no resultant force acting in the direction of flow. So, resolving all the forces in the direction of flow. So, the forces are the weight of the water whose component along the direction of flow and frictional resistance. These two forces should be resolved along the direction of flow and they can be summed up. So, here motion is in this direction and frictional resistance is in opposite direction. So, motion is WAL sin I, that is the weight component of rate of the water along the direction of motion minus sign for the frictional force since it is in opposite direction, that is frictional force into perimeter into length into V square. So bringing this term to the other side, we get V square is equal to W by F into A into P into sin I. So that means V is equal to square root of W by F into square root of A by P into sin I. Here, velocity V, we got the equation. Then we know that area divided by perimeter, that is equal to M, which is the hydraulic mean depth or hydraulic radius, that we already know. And square root of W by F, that is specific weight of water, divided by frictional coefficient, is given by Chassis constant C. Okay, so substituting the values of A by P and square root of W by F in the equation 3. This is equation 3. We get V is equal to C into square root of M into sin I. So for small values of I, that is I is an angle, I can have values from 0 degree to 90 degree or 180 degree or 360 degree. So for smaller values of I, like 0 degree and 1 degree, sin I tends to be equal to tan I. Okay, so that means it is also equal to I. Okay, that means sin 0 is 0. So V is equal to C into square root of M into I. Because the bed slope I is the bed slope, that will usually have very small values. So for smaller values of I, sin I will tend to tan I, which is again tending to I. So V is equal to C into square root of M into sin I replaced by I, since the value of I is very small. I is the inclination of the bed of the channel or the slope of the bed of the channel. So Q is the discharge, which is equal to area into velocity. Here velocity is given by C into square root of Mi. Now let's see a problem. Find the velocity of flow and rate of flow of water through a rectangular channel of 6 meter width and 3 meter depth when it is running full. That means water is running along the entire depth and width of the channel. The channel is having bed slope as 1 in 2000. Take Chassis constant C is equal to 55. So the solution is width of the rectangular channel is denoted by B, 6 meters given in the question. Depth is given by 3 meters D. Area is, here it is mentioned, it is a rectangular channel. Rectangular means area is B into D. B into D. That means 6 into 3, which is equal to 18 square meters. Bed slope is I, which is given by 1 in 2000. That means 1 by 2000. Chassis constant C is given as 55. Okay. Then perimeter. Okay. Perimeter for a rectangle. Perimeter is, if this is the breadth B and this is the depth D, perimeter is given by B plus D the whole multiplied by 2. But here we know that water is flowing under constant pressure. That is atmospheric pressure. That means it is an open channel. So that means this surface is exposed to atmosphere. So perimeter is B plus 2D. That is the top surface, there is no covering or there is no perimeter of the channel. Top surface is exposed to atmosphere. This is atmospheric pressure, right? Atmospheric pressure. So perimeter is B plus D plus D. That is B plus 2D, which is equal to 6 plus 2 into 3. That is 12 meters. So since this is an open channel, the top surface is exposed to atmosphere. Hence perimeter is the sum of the width of the bottom surface and depth at the sides of the rectangular channel. Hydraulic mean depth M is equal to A by P. So A is equal to 18 and P is equal to 12. So that is 1.5 meters. So here perimeter refers to the wetted perimeter. Okay. Velocity of flow is given by the equation c into square root of mi that we have seen before. So substituting the values of c, m and I, we get velocity is equal to 1.506 meters per second, and rate of flow, which is asked in the question, right? Velocity and rate of flow is asked in the question. Rate of flow is given by q is equal to v by area, v into area, that is 27.108 meter cube per second. Next problem. A flow of water of 100 liters per second flows down in a rectangular flue of width 600 mm. Flue means a channel and having adjustable bottom slope. If Chassis constant C is 56, find the bottom slope necessary for uniform flow with a depth of flow of 300 millimeters. Also find the conveyance K of the flue. Okay. Here it's given that discharge is equal to 100 liters per second. So we convert that to meter cube per second by dividing by 1000. So we get 0.1 meter cube per second. Converted liters per second to meter cube per second. Width of the channel 0.6 meters. Depth of flow 0.3 meters. Area of flow A is equal to B into D, which is 0.18 meter square. Here also the channel is of rectangular cross section, hence area is B into D. Okay, Chassis constant is given by C is equal to 56. So slope of the bed, it is assumed as I. Okay, and then hydraulic mean depth M is equal to A by P. So A we have here, P is B plus 2 into D, that is 1.2. Hence we get M as 0.15 meters. So using equation 16.5 that we have derived earlier, we know that Q is equal to area into velocity, that is A into C into square root of mi. So substituting all the values here, we get I, which is equal to, this is a very small number, so we convert that to fraction, that is 1 by 1524. Okay, hence slope of bed is 1 in 1524. So we have to find out K, which is the conveyance of the channel. Okay, here Q is equal to A into C into square root of mi. So K is A into C into square root of m. This quantity is called K, which is the conveyance of the channel section. So substituting the values of A, C and m, you get K, which is the conveyance of the channel. You can try this problem and submit.